Hello, Mr. Collier here. Today I want to give you some sample problems for projectile motion. A projectile is something that's moving in both the x and the y direction at the same time. So when we solve for projectile motion problems, we're going to need two sets of variables. For example, we're going to need how much it's accelerating in the x direction and how much it's accelerating in the y direction. The horizontal motion and the vertical motion are independent of each other, so we're going to need to treat them like two separate problems. There are a couple of features that every problem will have, though. The acceleration will always be negative 9.8 meters per second in the y direction, and the acceleration will always be 0 in the horizontal direction because the object will be moving at a constant speed. And one thing that they will share, though, is that the vertical motion and the horizontal motion will take the same amount of time, so they always have the same t. I'm going to do three problems in this review. I'm going to do a horizontally launched object that's just sort of falling. I'm going to do an angled launch that is returning to its initial height. And I'm going to do an angled launch that goes to a new height. So here's our first problem. This is a horizontal launch. If you shoot a bullet at 380 meters per second, how high should you hold the gun off the ground so you hit a target that is 1 meter high and 100 meters away? So this is an object that is going to be moving but also falling while it moves. As soon as it leaves the barrel of the gun, it will start to fall. So we're going to have to hold it higher than 1 meter off the ground for it to be a meter off the ground when it's 100 meters away. So the first thing we're going to do in this problem is to calculate how long it will take to travel 100 meters. Then we'll use that time to figure out how much the bullet will drop while it travels that 100 meters. To do this, we know that the initial velocity in the x direction is 380 meters per second, and we know it's not accelerating in the x direction, and it's going to travel 100 meters in the x direction. Again, as you do these problems, it's really important to identify what things are happening in the x direction, left and right, and which one are relevant to the up and down motion. With those three variables, we can solve for the amount of time that it takes the bullet to travel the 100 meters to the target. I plug in my numbers and I find that it takes 0.263 seconds for the bullet to travel 100 meters, traveling at 380 meters per second. With that information, I can figure out how much the bullet will drop as it travels those 100 meters. I'm going to use that same time because the amount of time it takes to travel the 100 meters is also how long it will take to drop some distance. That's the unknown, how much drop the bullet experiences in those 0.263 seconds. I actually end up using the same kinematic equation, only now what I know and what I don't know is a little different, and it's in the y direction. I plug in my values, and I solve for my delta y. Now this is saying that I have a negative delta y, and the way that I would interpret that is that the bullet is dropping. And how much does it drop? 0.339 meters. So now I'm going to put that together with the fact that the target is a meter off the ground, and when I give my final answer, it will be 1.34 meters off the ground. Again, that's the 1 meter that the target is off the ground, plus the amount that the bullet will drop over the course of those 100 meters. Now I want to talk a little bit about angled launches. In an angled launch, you have an object that is not just falling, it is also moving up and down. The initial velocity is at some angle. We use the letter theta to represent that. And that means that the object is moving both up and down and left and right. And we can treat it much like you would treat a triangle. The y component of this motion, which would be here, how much the object is moving up and down, is opposite to the original launch. And so that is going to be calculated using sine. The x component of the motion is adjacent to the angle. And so that is calculated using cosine. And so ultimately what it's going to look like is this. The initial velocity in the y direction is equal to the initial velocity times the sine of the angle that the object is launched at. And in the x direction, we simply use cosine instead. So those are going to be key for figuring out what the motion of the object is. Because the initial launch is at an angle, you've got some aspect of that launch is horizontal and some aspect of that launch is vertical. By breaking it down, we can analyze both independently. One last thing to consider as we do angled launches is that you want to make sure that your calculator is in degree mode. If you've got it in radian mode, that is going to give you some incorrect answers. So now let's look at a sample problem of an angled launch. In this case, we have a place kicker giving a football an initial speed of 20 meters per second at an angle of 35 degrees above the horizontal. What's the maximum height the ball reaches and how far downfield does it land? So if we picture this for a minute, we've got a ball being kicked. So some aspect of that kick is making it go left and right. That's the initial velocity in the x direction. And some element of that kick is making it go up and down. That's the initial velocity in the y direction. We're going to break that motion into those two components and then analyze the motion. So the x component is going to be used by taking the initial velocity 20 and multiplying it by the cosine of the angle that it's kicked at. That gives us an initial x velocity of 16.4. For the y component, we're going to multiply it by the sine of the angle instead, and we'll get 11.5. Knowing this, we can now figure the maximum height the ball reaches and how far it goes. For the maximum height, we're going to be talking about the y direction, so I'm going to be using all y variables. I'll take the initial speed in the y direction, that good old trusty negative 9.8 meters per second squared is acceleration, and here is where a little thought process comes in. At the apex, that's when it's going to reach its maximum height. And at the apex, the velocity in the y direction is 0. In other words, it's neither rising nor falling. For that brief moment in time, it has reached a 0 velocity in the y. With those three variables, we can figure out the maximum height. And we can also figure out the time. So for the maximum height, so first we're actually going to solve for the time. We're going to use this equation, Vf equals Vi plus At. We take our initial velocity in the y, our acceleration, and that'll tell us how long the ball is in the air. The time that you get from this is the time to the apex. If you want to know the total time, and again this works because we are returning to our initial height, is going to simply be double that. So we just take our time that we find, multiply it by 2, and that gives us the total time. Knowing that time, we can now solve for the apex. We can solve what the delta y is, how high it is, using the delta y equals Vft minus 1/2 At squared. I choose that equation because since my Vf is 0, it kind of cancels that out, makes it a little easier to solve. Plug in my values, and I find that the ball will rise to 6.71 meters above the ground. The last thing to calculate then is how far downfield it's going to land. So to do downfield, that's its x range, so I'm going to use its x values, and I'm going to use the equation delta x equals Vit plus 1/2 At squared. Now I know that in the x direction it's not accelerating, so this value here becomes 0, and all I'm left with is that Vit. The Vi is now, again, in the x direction. This is a common mistake students make, is they forget to switch it up. We're now talking about the x direction. And the second mistake students make is that now the projectile goes the whole up and down. So we're not just using the time to the apex anymore. Now we want the total time for this entire trip. That's why I used the 2.34 seconds. Plug those in and solve, and I find that it goes 38.4 meters down the field. So that's how you approach an angled launch, returning to the initial height. The final sample problem I want to show you is a little bit more complicated. We're going to do an angled launch that does not return to its initial height. So here you sneak to the roof of C-Pod, which is 20 meters tall, throw a water balloon at 15 meters per second at an angle of 25 degrees. Does it splash Mr. Collier, who is 40 meters away? And here's the part that makes it really complicated, what's its velocity when it lands? That's going to require a little extra calculation. So the first thing we're going to do is figure out how long does it take this ball, or balloon, to hit the ground. We want to figure out its initial velocity in the x and the y, just like we did in the previous problem. We're going to take the cosine for the x value and the sine for the y value. So now we have an initial x speed and an initial y speed. How fast it's going up, how fast it's going over. Now we're going to take those y values to figure out how long it's going to take to reach the ground. In the previous question, we had our delta y equal to the apex. Here, we're going to do the total delta y, which is that it goes from the top of the building up and then down again. So the delta y is simply the 20 meters that it falls. Knowing that, with the initial upward velocity, we can calculate the amount of time that it takes. Now, when you plug this into the equation, you have two options. You could solve for the VF in the y direction, or you can use the quadratic to get t. So I'm going to choose to use the quadratic right now, and I'm going to use delta y equals VIT plus 1/2 AT squared. When I plug my numbers in, I'm going to get the variable t in two different places, once squared and once not. And so to solve that, I'm going to have to rearrange it so that it's equal to 0, and then I can use the quadratic equation. When I get that, I'll get 2 times. One of them will be negative, so I'm going to throw that one out and keep the positive value. That positive time is how long it will take the water balloon to fall. Now, for displacement in the x direction, it's fairly simple now that I know the time. I'm simply going to take the speed in the x direction, which I calculated previously. I know that it's not accelerating in the x direction, and I'm going to figure out its displacement in 2.8 seconds. So I use my delta x equals VIT. Again, the acceleration goes to 0. And I have a final value of 38.1 meters, which is a little less than 40 meters away, but I think it's safe to say that we're going to splash Mr. Collier with that balloon. The final component to this is to figure out the final velocity. Now, the final velocity is made up of an x and a y component, and we're going to have to put those together. The VI in the y direction is 6.3, and the acceleration is negative 9.8. We know it's displacement. These are all values we calculated earlier. Now, with the time, I can easily calculate the final velocity in the y direction. Pick an equation, plug my numbers in, and I have a final velocity in the y direction. The final velocity is going to be negative in the y direction, and that makes sense since by the time it hits the ground, it's going to be falling downward. The final velocity in the x direction is the same as the initial velocity in the x direction because it's not accelerating. So I actually don't need to do any math. I just take that same number that I started with. Now I need to turn this into a final velocity by combining these. We're going to combine them in a right triangle. We're going to combine them based on the final velocity in the y direction, the final velocity in the x direction, and the overall final velocity will be the hypotenuse of this triangle. So we're going to use VF squared equals VFX squared plus VFY squared to solve for the final velocity. Now, it's 25.1 meters per second, and that could be positive or negative. We're going to make it negative since it's going downward. And then if we want to find the angle that we're using, it's going to be the opposite and adjacent values that we know, so we'll use the tangent, and we get a negative value. So we're going to use that negative value to say that the balloon is going downward. So it's 25.1 meters per second. You can call that negative if you like, although the angle really shows the direction as well as you need to. 57 degrees below the horizontal. So take a second to look that over because I realize this is a little complicated, that we're sort of taking these x and y components and putting them together to make a final velocity. We're using the a squared plus b squared equals c squared. Then we're also, to figure out the angle that they make, we are using a tangent, and then we're putting it all together to have one final velocity vector. So those are the 3 types of problems. Good luck, and let me know if you have any questions.